Yeah, let's start. So, good afternoon, ladies and gentlemen. Let me introduce today's speaker, Milan Pokorny. So, let me start from beginning, yeah, not completely beginning, but more or less. So, he did his study at the Charles University, the Faculty of Mathematics and Physics, and he did this diploma thesis under supervision of Professor Necas. Then he moved to his beautiful place Olomouc, and he was there as an assistant in Department of Mathematical Analysis, this Palacký University. And parallelly, he did his test kotutel. It means between in Czech and in Faculty of Mathematics and Physics under supervision of Professor Necas, and then in Toulon under supervision of Professor Antonino Novotny. This was finished, let's say, 99, 2000, and then he realized that Prague is also beautiful, and then he moved back to Prague. Of course, unfortunately, not to academy, but at least he's in Prague, and he is at Faculty of Mathematics and Physics. Then, from 2006, he became vice head of Institute of Mathematical Institute, but not of academy, but of Charles University. So there are two institutes of mathematics. 2008, he became associate professor. Now, if I'm right, 2020, you defend your big doctorate degree thesis. And also in this year, he found his courage to be head of whole mathematical institute of Charles University. And today he will speak about very nice subject about homogenization for compressible Navier-Stokes Fourier system in domains with tiny holes. So please.
Okay, Sharka, thank you very much for a nice introduction. And before starting, I would like to say that this is a joint work together with Yong Lu, who actually introduced me to this subject during my stay at the University of Nanjing 2019. And then the continuation for evolutionary problem is with my PhD student, Emil Skřižovský. So what we will understand under homogenization. So our domain will be a domain with many tiny holes. So we have our omega here, and we have many small holes which do not touch each other, which are inside. And the situation is that always in some small box with diameter epsilon, inside there is this small hole with diameter epsilon to power alpha, where alpha will be strictly larger than 1 and even larger than 3 and so on, depends on the problem. And so these holes do not touch other. They are not necessarily periodic, but they are not too far from being periodic. And the question is, what happens if the number of these small holes will go to infinity, but also at the same moment they will become smaller and smaller, which means the limit when epsilon goes to 0. So this problem is very well understood in the case of incompressible Stokes or Navier-Stokes system. There are results by Allaire, who actually proved that in case when alpha, recall that alpha is this power, so basically it defines the smallness of the holes. So if alpha is between 1 and 3, strictly less than 3, then the limit system is the Darcy system. If alpha equals 3, so this is in some sense a critical exponent, so the limit system is the Brinkmann system. And if alpha is larger than 3, so in the limit we get the same system of equations. This was for the steady problem. For the evolutionary problem, Similar result can be found in the paper by Eduard Fajezel, Juliana Mlejeva, and Šárka Nečasová. Concerning the compressible Navier-Stokes equations, so probably the first result in this direction is due to Nader-Mahmoudi in the case alpha equals 1, which was later on extended by Eduard Fajezel, Antonín Novotný, and Takeo Takahashi. And in all cases, the limit system is a version of Darcy equations for porous medium. For tiny holes, so alpha larger than 3, for the steady compressible Navier-Stokes equations, there are papers by Eduard Fajezel, Yonglu, and Lars Diening, Eduard Fajezel, and Yonglu, who prove that in the limit we get again the steady compressible Navier-Stokes equations. I will actually use partly their results. For the evolutionary case, there is a paper by Yonglu and Sebastian Schwarzacher, where for gamma sufficiently large, actually the lower limit is 6. They can show that for the evolutionary problem, again, the limit system is the same. It means compressible Navier-Stokes equations. So we will consider the compressible Navier-Stokes Fourier equation. So there will be extra difficulty with the temperature. And the presentation is based on 2 papers. The first one has been recently published in the Journal of Differential Equations, and it deals with the stationary Navier-Stokes Fourier system. And recently submitted paper concerning the evolutionary system. So what is the outline of the talk? So first, I would like to speak about the steady case, and I will actually mostly speak about this because it's technically slightly less difficult and easier to write. So I will start with the formulation of the problem in the original omega epsilon. So this is actually a series of domains. I will formulate the main result, and I will speak about the proof of the main results. In particular, I will speak about estimates which are independent of epsilon. First, for the functions defined in omega epsilon. Then I will speak about suitable extensions to the whole omega and estimates of extended functions. Then limit passage, and in particular, the problematic terms are here properties of temperature and entropy inequality. Indeed, there is the standard difficulty for the steady compressible problem, namely strong convergence of the density, but this is more or less very similar to the standard situation when one wants to prove the existence of solutions. And then I will mention the evolutionary case, mainly formulation of the main result and few differences which are needed in the proof. So we start with, let's say, classical formulation of the problem in the domain with holes. So I will consider the steady compressible Navier-Stokes equation. So the first equation is the balance of mass or continuity equation. The second equation is the balance of linear momentum. And the third equation is the balance of the total energy. Rho is the density, U is the velocity field, P is the pressure, and it is a given function of the density and the temperature theta. S is the stress tensor, capital E is the total energy, and Q is the heat flux. F is given force. We include boundary conditions, and for simplicity, we will assume that U equals 0 on the boundary, so homogeneous Dirichlet boundary conditions, and we consider that the heat flux is proportional to the difference between the temperature outside and the temperature inside. And finally, we have to prescribe the total mass. Note that actually we cannot prescribe q.n equals 0, or we can, but then the situation is not extremely interesting, because in case we consider the study problem as a limit of the evolutionary system, so there are not too many possibilities either. F is gradient of some potential, and in this case the solution is u equals 0, temperature is a constant, and rho is a solution of certain first order partial differential equations, which has certain properties independence of this potential to the force. Or in general, it may happen that if F is not potential, then the energy goes to infinity, and one cannot hope for any stationary solution as a limit of the evolutionary problem when time approaches infinity, and probably this solution may even not exist. That's why we must allow some energy exchange on the boundary, and the easiest situation is given by our boundary condition for the heat flux. Okay, so density will be assumed to be non-negative, not only positive, because it may easily happen that the steady system has a solution with density which is equal to 0 even on a positive, on a part of the domain with positive measure. This may easily happen, and the temperature will be positive, and velocity is a given field, or field which we would like to find. So what will be our constitutive relations? So the pressure will be rho to power gamma plus rho theta. For simplicity, we can assume more complex pressure law with asymptotics as is given here. But in order to make everything as simple as possible, we just stay with this formulation. And the bound for gamma, so gamma larger than 2, is connected with the homogenization, because for the steady problem, we are able to prove existence of a solution even for gamma larger than 1. For the stress tensor, we will assume that our fluid is Newtonian. So we will assume that it has the given form here, where mu and nu are the viscosities. So the shear viscosity is a given function of the temperature, which is globally Lipschitz continuous, while the bulk viscosity nu is just a continuous function. So mu behaves like 1 plus temperature. Nu is bounded from above by something like 1 plus temperature, and can even be 0. There is no problem with this situation. The heat flux is assumed to fulfill the Fourier law with the heat conductivity, which behaves like 1 plus temperature to some power m, where due to the homogenization, we will have to assume that m is larger than 2. In general, for the existence, we can treat the situation up to 2/3. Just for simplicity, we will actually assume that the kappa is just 1 plus theta to m. It will simplify certain technical steps. The specific total energy is a sum of specific internal energy, small e, and specific kinetic energy, 1/2 u squared, where the specific internal energy satisfies the Gibbs law. The Gibbs law says that if we take the total differential of the internal energy and we add the pressure multiplied by total energy of 1 over rho, then this is not a total differential. This is, we have to divide this by the temperature, and then we get a total differential of a new function of specific entropy. And this Gibbs relation gives us that the internal energy has two parts: one which has precisely this form, and another one where this is unknown function of the temperature. And in our case, we, for simplicity, take the linear function of the temperature. So using this Gibbs relation, we can show that the entropy fulfills formally this equality. Formally means that assuming that everything is smooth, we can we can subtract from the total energy balance the kinetic energy balance, and then divide it by theta, do some manipulations, and we end up with this formal equation. Indeed, we are not able to guarantee existence of classical solutions unless we go to the situation when the data are small or close to some equilibrium. This is something we want to avoid, so we will consider only weak solutions. So existence of weak solutions is guaranteed under certain technical assumptions, and there is no restriction on the size of the data. So first, the weak formulation of the continuity equation is as given in equality 16, where the test functions are arbitrary, smooth, compactly supported functions in R3. It means that we may extend both the velocity and the density by zero outside of the omega epsilon, and we get this formulation. An important role for those who know the problems in compressible fluid mechanics is the renormalized continuity equation, which at the end helps to show strong convergence of the density. Formally, if you consider the equation divergence of rho u equals 0, you multiply this by b prime of rho, and you do manipulation. So you look at this as rho diff u plus u dot gradient of rho. So you get u dot gradient of b rho, then b prime of rho divergence of u, and you may rewrite it into this form. Again, everything is extended by zero outside of the domain omega, and we can get this formulation. And B is arbitrary sufficiently regular function. Finally, next, the momentum equation is just the momentum equation multiplied by smooth, compactly supported function, and we integrate by parts in several terms, and we end up with this formulation. More delicate is the question of correct formulation of the energy balance. So the first possibility is to consider the total energy balance, which in our case is just multiplying by smooth function, which is smooth up to the boundary, performing certain integration by parts using the boundary conditions, and we end up with this formulation. So this is one possibility. There is in general another possibility to consider just the internal energy balance, but this is not so much suitable because then we get a nonlinear term in gradient of u, and there are problems to fulfill it. There are very rare situations when one can really get that the internal energy balance is satisfied. On the other hand, if you recall the form of capital E, so capital E involves a term which is u squared. So here is also a term something like rho u cubed formally, which means that if I mean, I will now be a little bit faster. So what you can get for the velocity is usually just W12 estimate, which means by embedding L6 because we are in three space dimensions. So this term is only in L2. And therefore, to get this term really integrable means that it makes sense only if the density is at least square integrable, which means that there are problems with small gammas, and then this formulation is not suitable. Therefore, another possibility is to not to use the total energy balance, but to use the entropy inequality. So the entropy inequality means that we already had entropy identity. Unfortunately, but this is also physically relevant, we cannot prove entropy equality, but rather inequality. So mathematically, the reason is connected with some convergences. Okay, I see that there are some terms missing. There is missing gradient of u here. So this term is only L1, and we have problems really to pass to the limit here, and we must use weak lower semi-continuity. Similar problem is also in the other term. So that's why we can prove only entropy inequality. And if we use part information from the total energy balance, namely, if we use also only the case when the test function psi is equal to 1, we can get also a relevant formulation based on entropy inequality and partial information coming from the total energy balance. So this is another possibility of formulation of the total energy, which is compatible with the strong solution in the sense that if we have sufficiently regular solution fulfilling these two, one identity, one inequality, we get again smooth solution to our original problem. We will not face this problem here because our gamma will be actually larger than 2, but this is just to understand that there are possibilities to work with this energy balance in different ways. And as I will say a bit later, this is not the case in the evolutionary problem. So what is our weak solution? Our weak solution is a triple rho u theta. The density is non-negative, temperature positive. The functions are sufficiently regular so that all these integrals are meaningful. The mass is prescribed, and we have satisfied all equalities, including total energy balance and including entropy inequality. And for gamma larger than 2, we are able to show that such a solution exists even for gamma larger than 5/3 and m larger than 1. And this proof can be found in a paper together with Antonín Novotný or in an overview paper with Piotr Mucha and Ewelina Zatorska in this Handbook of Mathematical Analysis edited by Antonín Novotný and Giga. So what is our aim? So now we would like to pass with epsilon to 0. And we would like to show that under certain assumptions, the limit is the same system. So we get again the compressible Navier-Stokes equations. However, now in the full domain omega. So we have certain assumptions. So F is immediately given on the whole domain. The masses do not go to 0. Okay, they could go to 0, but then the solution can be just equal to, I mean, the mass, total mass equal to 0, and this is something which is not very interesting. So we assume that the mass is bounded from above and also from below, strictly away from 0. And we have some technical assumption on the boundary temperature theta naught. And we assume that we have suitably extended functions rho epsilon, u epsilon, and theta epsilon. I will speak about this in a moment, to the whole omega. And then for sufficiently large alpha, m, and gamma, fulfilling in particular this inequality, we get modulo a subsequence, epsilon going to 0, that we have boundedness of the solutions on each omega epsilon, and then in the limit we get again solution to the original compressible Navier-Stokes equations in the whole domain omega, with density which is non-negative and temperature which is positive almost everywhere in omega. So this is the result which we wanted to prove. Look that somehow the holes must be very, very tiny if gamma approaches 2 or m approaches 2, because then the lower bound on alpha blows up. Okay, so what will be our proof? We would like to start with estimates which are independent of epsilon. So what we can do, we can return to the entropy inequality and take the test function psi equals 1. If we do so, so we get rid of these terms. This is something which we will be able to bound, because this length of or the area of this the omega epsilon is finite, and the rest is just what we can get an information for, and we end up with nice estimates for the velocity, and that's actually all we can get. Some informations for the temperature. In particular, we control the gradient of the temperature, gradient of logarithm of the temperature, gradient of some temperature to some power, and 1 over temperature on the boundary. But we are not able to control the temperature, but we can read some information for the temperature just from the equation from this remainder of the total energy balance. However, the bound depends on the density. It's coming from something like rho epsilon, u epsilon. We estimate this in L6, and this we have in L6 over 5. So what we need further, we have to find some nice bound for the sequence of densities, because we have to control anyway the density, and also we need it in order to control the temperature. We need to check that formal embedding coming from this term, which formally gives some L3m estimate of the sequence of temperatures, is really independent of epsilon, because the domains omega epsilon are not uniformly Lipschitz. So we must show it by some other argument than direct use of Sobolev embedding theorem. And we have to extend all functions to the whole omega so that we keep all these uniform bounds. So we start with the extensions. And if you recall what I said about the continuity equation, that we may extend the velocity and the density by 0 and keep basically the formulation in the whole R3. So this means that this should be a reasonable extension for velocity and for density, because we simply keep the norms, so the norms do not change, and we are basically done with the velocity, because we get, after this extension, the velocity remains in W12 0 omega now, and the bound is uniform with respect to epsilon. On the other hand, even though we know that the density, the LR norm in omega, is the same as LR norm in omega epsilon. It doesn't say anything about the uniform bound of the sequence of densities because we do not control rho epsilon up to now in omega epsilon. So we have to find a control of this sequence of densities. First, and finally, extension of the temperature. Extension of the temperature is based on some classical results due to Cioranescu and Paulin, where it was used for homogenization with Neumann boundary conditions for Laplace equation. So we can use more or less the same extension operator with one modification. So this extension operator allows us to extend the function that it remains in W12. We control the L2 norm of the gradient. We also control arbitrary LQ norm by LQ norm of the original function away from the holes. And we can modify the operator in such a way that if we have functions which are non-negative, so we may extend them to functions which are non-negative in the whole omega. I will not speak about this. I will rather speak about application of these extensions. Okay. So what we know that this extension of the temperature, this tilde means that this is the extension which keeps the sign, so the extension is non-negative, even though we are not able to construct this extension directly, being almost everywhere positive. So it may happen that the extension is somewhere zero, but it doesn't matter because we will actually show that in the limit function will be positive. So we have this bound. We know that this constant is independent of epsilon. However, the proof is not immediate because, as I said, the problematic term is here that we are not able to use the Sobolev embedding theorem, and we must proceed a little bit differently. Namely, first of all, we can use that the extension near the boundary d omega is actually the same as the original function because the holes do not touch the boundary. So this is important. So this means that we control the gradient. Very good. And we also control the L2 norm because L2 norm of the function is controlled by the gradient and L1 norm on the boundary in the whole omega. But here, this function extended temperature is the same as the temperature itself. So this and these are the same functions. And this we know that we can bound by the density. So using this, we know that our extended function is actually in W12 in omega. But in omega, this is now fixed domain, and we may use in omega the Sobolev embedding theorem. And the Sobolev embedding theorem gives us that we have L6 bound of the extended temperature in the whole omega by the density, which is this bound. On the other hand, we know that this extended function and the original function, the original temperature, are the same in omega epsilon. So the temperature theta epsilon in L6 omega epsilon is actually the extension, but restricted to omega epsilon. And this is bounded by the density. So we have at least L6 bound for the temperature. This is not enough because our m will be larger than 2, so we must go further. And this is now actually bootstrap argument. So we take Q1. Q1 will be minimum of 6 or m, and we compute this estimate. We know that this estimate is valid. This is coming from our, if we interpolate the information coming from the entropy inequality. That's why we know that also the extension of this function, but be careful, the extension of this function may be different than extension of theta epsilon. So these may be two different extensions, but anyway, this extension satisfies this inequality. Again, we use the information which we have here. So we can use Sobolev embedding in omega, and by Sobolev embedding, we know that we have this inequality. And we use again the fact that the extension actually coincides with the original temperature in omega epsilon. So that's why we get the control of theta epsilon in L3Q1, and we iterate the procedure until we reach the value of m. So finally, we really get this information. As soon as we have this information, so we can get, now it's not probably well seen, but we control the extended temperature in L3M in omega by the right-hand side, by the L6/5 norm of the density. So what is needed now are some estimates of the density. So there is a well-known procedure based on so-called Bogovsky operator if we have a fixed domain. But here we are in a little bit different situation because the domain actually depends on epsilon. But in the paper by Lars Diening, Eduard Faresel, and Jon Glu, the authors showed a very nice construction of Bogovsky operator, which exactly corresponds to our situation. And it is possible to show that this Bogovsky operator fulfills, so this is a solution operator to divergence of u equals f with u on the boundary equals 0. So this is this Bogovsky operator, but now we should be careful, we have omega epsilon. And it can be shown that we have the standard control for the right-hand side, which has 0 mean. This is this 0 here, where the dependence can be explicitly computed on epsilon. And in certain regimes, it can be shown that this exponent at epsilon is actually non-negative. So that's why it doesn't blow up. So if we use precisely this construction of the Bogovsky operator, we can show that the sequence of densities is bounded in some L gamma plus some positive theta in omega epsilon, where theta can be computed as a minimum of 2 gamma minus 3 and something which also depends on m. And the proof is based on application of such a test function in the momentum equation. Indeed, we have to subtract the mean value because we need that the function on the right-hand side must have 0 mean. The proof is a little bit technical and I will not speak about this here. So we end up with these estimates in the whole, in omega epsilon. So we control temperature, density, velocity in different norms. The constants are now independent of epsilon. Okay. We will now extend our functions. So the temperature by this extension E epsilon or E epsilon tilde and for the temperature is E epsilon tilde, and rho epsilon U epsilon by 0. And I will, in order to avoid too many notation, I will simply write U epsilon, rho epsilon, and theta epsilon also for the whole omega. We can compute also trace estimates of the temperature, which are needed to control the boundary terms. And the final information is that the L2M norm may blow up because of the number of the components, but altogether the area of these boundaries goes to 0 when epsilon goes to 0. So finally it will kill this term, which doesn't blow up too fast. So what is the situation? We have a sequence of velocities converging weakly in W1 to 0 and strongly in LR. The densities weakly in L gamma plus theta, and temperatures weakly in W1 2 and strongly in LR. And we would like to show that the triple rho U theta solves our original problem. So we can write that if we extend the functions and we try to write the equations in omega, so formally we get formulation with rho epsilon, theta epsilon, and U epsilon in the whole omega. So there will be some terms, some remainder, this, and this. So these are these two. And we can show that these terms actually go to 0 when epsilon goes to 0. I will not speak much about this. And in the limit, we can get formulation of the total energy balance. However, here in the internal energy and here in the pressure, we have just bars. This is connected with the fact that the pressure converges only weakly, and we will be able to remove these bars, which denote the weak limit of the corresponding sequences, as soon as we will be able to show that the density converges strongly. Next point is that using the properties of extension, and here is a mistake, there shouldn't be this tilde, and using the control of extension of the logarithm, but the extension of the logarithm is without tilde. So logarithm is a function which can be negative, so I don't want to cut it off somehow and so on. Simply the extension of the temperature is bounded in L2, and using this and some properties of these domains omega epsilon, I can show that in the limit the temperature is positive, and also we can show that E epsilon of logarithm of theta epsilon converges strongly to logarithm of theta. For example, in L2 omega. What is a little bit more complicated, and I will spend some time on it, is the limit passage in the entropy inequality. Because for the entropy inequality, there are several terms which in the standard existence proofs are just controlled by the weak-lower semi-continuity, and in some situations we may get into troubles with extensions. So as I said, because of these computations, I will assume that the heat conductivity is just 1 plus z to power m. So I will now work with two types of extensions of temperature. For the temperature itself, I will use this notation, and for logarithm of temperature, I will use this notation. This is just to see the difference where I use the non-negative cutoff and where I don't use it. And now, again, the aim is that I would like to write something like entropy inequality and some remainder, where I will be able to show that the remainder goes to zero. Note that there is no problem with extension of this term of this entropy, because here is u epsilon, rho epsilon. So even though the theta epsilon is not extended by zero, the whole term can be extended by zero, because there are terms like logarithm of rho epsilon and logarithm of theta epsilon. But I can understand it in the sense that it is as a total extended by zero. So the complications come from this term, because this term, there are some problems with how to rewrite it in a way that we get in the limit inequality. As I said already, we will use the fact that E epsilon logarithm of theta epsilon converges to logarithm of theta almost everywhere or in L2. And the trick is following. Originally, I will speak only about the first term, the second term is the same. Originally, I start with a term like this. And I rewrite it for some positive delta, and finally I will pass with delta to zero as exactly this term, but with power 2 minus delta. And then I have here the gradient, where the gradient is larger than 1, here where it is less or equal than 1. So this together cancels this term, and then I have this term. So this is my I1, I2, and I3. And I want to show first that I may first pass with epsilon to 0 and then with delta to 0, and in the limit I get the correct inequality. So I1 is easy, because if delta is fixed positive, then I know that this difference, omega minus omega epsilon, goes to 0 when epsilon goes to 0. So for fixed positive delta, this will go to 0. I3 is basically a difference of such functions. If I compute the maximum of this function between 0 and 1, because recall the difference we take only in the part where the gradient is less than 1. So the maximum does not depend on anything, it's just fixed number. And therefore, the bound for I3 is independent of epsilon. So we can bound it by something which does not depend on epsilon. And later on, when we pass with delta to 0, this goes to 0. So if we pass with epsilon to 0, we can get this inequality. So the C delta is coming from here, while here the I1 term disappeared. And now here we can pass with delta to 0. Since gradient of logarithm of theta is a L2 function, so here this goes strongly. This C delta disappears, and we get precisely what we wanted to have. Namely, this inequality. And exactly in the same way, we can also treat the other term. So we end up with the correct form of the entropy inequality, because all the other terms appearing in the remainder simply can be easily shown that they go to 0. So the only missing point is the strong convergence of the density. Okay, so we may now pass to the limit in all equations and then show the strong convergence of the equations. So for the continuity equation, it's very easy. For the continuity equation, we can get not only the weak formulation of the continuity equation, which is written here in the sense of distributions, but we can also show the renormalized continuity equation because the density is sufficiently regular. What is a little bit more tricky is the limit passage in the momentum equation. However, this is something which was treated already before in the paper by Lars Dinning, Eduard Feiereisel, and Jon Gru. So the main point is somehow we need to have a compactly supported test function. So we must solve the problem that we want to get from functions which are compactly supported in omega epsilon to functions which are compactly supported in omega. And this is based on these functions g epsilon, which can be constructed in such a way that we can control their norms with respect to epsilon. I will not speak much about this because this is rather technical, and but on the other hand, the same as in the case of Navier-Stokes equations. So this is the main result. The main result allows us to pass to the limit in the momentum equation, and the only missing information is the strong convergence of the density. But the strong convergence of the density is relatively well understood. Moreover, we are in the case when gamma is sufficiently large, so we have no technical obstacles here. So the proof is based on the validity of the effective viscous flux identity, which is here written for our case. On the validity of the renormalized continuity equation, both for this epsilon equation and in the limit, which in our case is for free. And using this, we can show that for a very particular function b of rho equals rho logarithm of rho, which is convex, not differentiable at 0, but doesn't matter, 0 at 0, we can show that this integral actually vanishes. Indeed, to show it, we must know that gamma is larger than 2, because we must know that this integral is well defined, but this is our case. Passing to the limit, we can show also this. So using the effective viscous flux identity here is very simple because it reduces only to this identity. And we now simply use the properties of convex functions and weak convergences, which in the end leads to the equality that rho to power gamma bar, so the weak limit of rho epsilon to power gamma, is actually rho to power gamma, which implies the strong convergence of the sequence of densities for in L1 or almost everywhere. This almost everywhere implies the strong convergence in arbitrary LR, where R is strictly less than the upper limit for the bound of the density. Okay, that's the end of the story concerning the steady problem. So we have still few minutes. So I can say very briefly what happens in the case of evolutionary problem. So the weak formulation of the evolutionary problem will come in a moment. So here I have just a classical formulation. So the main difference between the steady problem and the evolutionary problem is that we cannot generally show existence of solutions which satisfy the balance of total energy, and the less we can show it for the internal energy. And the best formulation, this is work of Antonín Novotný and Eduard Feiereisel, is the formulation in the sense of entropy. So we have entropy inequality, actually, as we shall see in a moment. Here we write it as equality with some entropy production rate, which I will introduce later. And we have together with this also the total energy. or energy equality, but global in the sense that it is integrated over omega epsilon. Here we have some initial conditions. We need to add boundary conditions. Again, the velocity will be 0 on the boundary, so homogeneous Dirichlet boundary condition, while for the heat flux now we can use the thermally insulated boundary condition, so Q dot N equals 0. Indeed, it's possible also to use the same boundary conditions as before. There is no problem with this. So we prescribe the initial conditions which play a role also in the energy equality. And what is the difference? The difference is that now we will have the same part of the pressure, but we have extra part which models the radiation according to the Stefan Boltzmann law. This term is important to get the strong convergence of the temperature, but I will not speak much about this. The situation is more or less the same as in the case of the proof of existence of weak solution for the evolutionary Navier-Stokes Fourier system based on entropy inequality. We have the stress tensor again of the same form as before. So the bulk viscosity can be equal to 0, while the shear viscosity is strictly positive, and both functions behave like 1 plus temperature. We have the same form of the heat flux, but here, since the heat flux is usually related with this Stefan Boltzmann law, so we use this relation and we take the power equal to 3 in this heat conductivity. And we have the total energy again as before. And using again the Gibbs relation, we end up with the internal energy, which has two parts. The first part is the same as in the steady case, and the last part corresponds to this extra theta to power 4 term in the pressure. For the entropy, we have this relation. Again, the first two terms are the same as before. The last one corresponds to this Stefan Boltzmann law. And the weak formulation is now for the continuity equation and for the momentum equation more or less the same as before, just taking into account the time derivative term and writing it with initial conditions here and initial conditions here. Again, we can extend rho and u by 0 outside of omega epsilon, and we get the formulation in the whole R3, which is standardly understood. Here, for the momentum balance, we have functions which are compactly supported in omega epsilon. For the energy, we can have equality or inequality. It doesn't matter for the proof. We have this situation. So this is just what we had before. E naught is the initial energy. And we have the entropy inequality. So the entropy inequality is again inequality because of the presence of this term, but this sigma has lower bound by these two terms. It's in general a non-negative radon measure, and we have this bound in the sense of measures. Again, definition of the weak solution is that if we have sufficiently regular functions, density is non-negative, even though we may expect that if we prescribe initial density, the density should remain positive. In general, this is open, and we only know that the density is non-negative. On the other hand, temperature is positive almost everywhere. In the time-space domain, we assume some regularity that all the terms which appear in the integrals are finite. Sorry for the misprint here. It should be W12. And the main theorem is that for gamma larger than 3/2, there exists a weak solution to our problem. The proof can be found in the very nice monograph by Eduard Feyreisler and Anthony Novotny. Even though the proof there is only for gamma equals 5/3, it can be simply easily extended. And the main result is that, again, on each omega epsilon, we can solve our problem. We can have some control. And if gamma is sufficiently large, okay, gamma larger than 6 is not very nice, but that's the situation. Alpha is sufficiently large and it blows up when gamma goes to 6. Then, if we know that our initial density is such that it is bounded away from 0 for each epsilon strictly by some constant. We have some convergences of the initial density, some technical assumption on the initial momentum and on the initial temperature. I will not comment much on it. So simply some reasonable assumptions that everything goes in the energy towards a limit which we would like to have. Then we have existence of the solution and we can pass to the limit, and in the limit we get a triple rho u theta, which is again a weak solution to our problem in the domain 0t cross omega. So exactly the result which we would like to prove. The procedure is more or less very similar. So first we read some a priori estimates. Using these a priori estimates, we need to get estimates, extra estimates of the densities. Here, all these estimates are uniform. There are no bounds which depend on density. On the other hand, we have only L infinity L1, L infinity L gamma, which is not enough to pass to the limit in the pressure. So to do it, we must again employ the Bogovsky operator. However, there is a technical problem here in the evolutionary problem because we need extra information about the Bogovsky operator, namely that it works also in this form. So if the right-hand side is in the form of divergence of something, so then simply this B epsilon kills the divergence in the sense of estimates. And the proof of this construction can be found in the paper by Yonglu and Sebastian Schwarzacher, which I already mentioned before. So doing some computations, we can show that we can control uniformly the density in LQ with Q 5/3 gamma minus 1 if gamma is below 33, or Q is below 18/11 gamma if gamma is above 33. Just as a remark, we must perform these computations in 2 steps. In the first step, we only get 3/2 of gamma, and then we can extend it based on using this information in the second computations. And the rest is more or less the same. And the only major difference is that we have to show in a different way the strong convergence of the density because of lack of compactness in time of the sequence of temperatures. The temperature is a little bit a troublemaker here because we control only rho epsilon theta epsilon in the sense of time derivative. And if we allow the density to be 0, which we cannot exclude, then we lose any information on the time derivative of this. But there is a, I would say, well-known procedure based on Diffker lemma, and which uses the presence of this extra term, theta to power 4, in the pressure. Okay, the conditions on gamma and alpha are a little bit complicated, but there are more or less related to the extensions of the momentum equation. know that historically, actually, we were not able to prove the convergence in the entropy inequality in the situation of the steady Navier-Stokes Fourier system. So that's why the paper Vision glue is without the entropy inequality. But we realized that we can do it using this trick which I explained before. And therefore, we were able also to attack the evolutionary case, and that's the result. And that's all. Thank you for your attention.
Thank you very much for your very nice talk. So great. Now there is the time for questions and remarks. So please go ahead.
Maria wants to ask something. You are muted, Maria.
So I maybe it's a standard question for you, but I'm wondering, in the heat flux you have this kappa of theta to be 1 plus theta to the power 3. Is this something very classical, or what is the reason for this form of the kappa?
Well, I am not a specialist. I just used that I found somewhere that it is somehow related to this presence of theta to power 4 term in the pressure.
Okay,
but I could. I mean, in the paper, I can treat basically arbitrary power m. There are some technical complications, but it can be done. However, there is some lower limit on this m, similarly as in the steady case.
Yeah, and what would be the lower 3 or something like that? Or the lower limit?
The lower limit, okay. I think it's more than 3. I don't remember now.